In this lecture, we'll be covering the concept of network delay, packet loss, and throughput in the network. As you know, a network consists of a number of hosts that are connected to each other through a set of routers. Every router along the way will have a buffer or a queue. This will be used to save packets if the link is busy or there is no way to send the packet at that moment. So these packets will be saved in a queue and sent later. Every queue has a limit, which means that, for example, a queue can handle this many packets. If there is no place to hold that packet in a queue, the packet will be dropped and marked as a lost packet. We'll talk about it later in details. When we look at the network, we have to consider 4 types of packet delays. The first one is the nodal processing delay. Every packet received at the router has to be checked for errors. The router, for example, has to look at the header of that packet to figure out where to send that packet. The router has to figure out the destination of the packet and check if it has a direct connection to the destination. If yes, it will send the packet. Otherwise, it has to forward it to another router that will try to get it to the destination. All this will take time and will be referred to it as a delay of the network. So this is our first delay, is the nodal processing delay. The next delay is the queuing delay, which is the time it takes the packet to wait to be transmitted on the link later. We have the transmission delay, which is the time it takes the packet to be put on the link to be transmitted between point A and point B. The packet delay or the transmission delay consists of, or can be measured by, the length of the packet in bits and the bandwidth, the link bandwidth, or the rate or the transmission rate of the link in bits per second. So the delay can be measured as the size or the length of the packet divided by the rate of the link. The second delay is the propagation delay. The propagation delay is the time it takes for the packet to be moved from point A to point B, being transmitted over the link. So the delay consists of the distance, which is the length of the physical length, and the propagation speed, which is close to the speed of light, 3 to the power of 10, or 3 multiplied by 10 to the power of 8 meter per second. And it can be measured as the distance divided by the propagation speed. There's a huge difference between the transmission and the propagation delay. Let's assume this is our packet. This is bit 0 or bit 1, and let's assume we have 10 bits. This is bit 10. The transmission delay is simply the time it takes to move all these bits from the queue to the link. Note that they're not moved yet to the next part or the next hop. They're just right here. The propagation delay is the time it takes us to move the whole packet from this point to the destination. That's the propagation delay. Let's go back to the queuing delay and discuss it in a little more details. As you recall, the link bandwidth is measured as bits per second, which is how many bits this link can transmit in a second. We have the length of the packet in bits. We have some new things, some new measurement is the average packet arrival rate, which is how fast these packets being arrived at this queue or at this router. The average rate at which bits arrive at the queue can be measured as the length multiplied by the packet arrival rate, and that will give us how many bits being received in a second at the queue. Now looking at the link bandwidth and the average arrival rate, we can come up with a new measurement called traffic intensity. Traffic intensity plays an important role in estimating the queuing delay, and this can be measured as the average arrival rate multiplied by or divided by the link bandwidth, which is LA multiplied by R, and that will give you the delay in milliseconds or second or milliseconds. Now let's look at this. The value of this traffic intensity will give us information about the delay in the network and what might happen to those packets. If the queuing delay is very small, that means the link bandwidth is fast enough to take all the packets as they arrive in the network. That means the arrival rate is close enough to the transmission rate, which means that every packet we receive will be put on the link and pushed to the other side. The same thing for the next packet and so forth. The problem is if the link bandwidth is not enough to handle all these packets being arrived, which is close to 1. What will happen here, you receive too many packets, but the link cannot handle all these packets. It's very slow, and that will create more delay in the queue. So all the packet has to wait till the link transmit the packet, then the next packet, then the next packet, and so forth. So all this delay in the queue will pile packets, and these packets might be dropped because there is no room left to handle more packets. So as a rule, when you design your network, make sure that you design your system so the traffic intensity is not greater than 1, because it will be infinity and it will be out of bound, and there will be a lot of delay in the network. Let's look at the internet delays and router. There's a program called Throughput. This program provides delay measurement from source to router along the end internet path toward the destination. As you know, a packet is being sent from source to destination, and along the path it might encounter a set of routers. The Throughput program can measure these delays by sending those special packets from source to the router and measure the time it takes. The Throughput will send 3 packets that will reach a router, and then the router will send that information back to the sender. The sender will measure the time it takes, or the time between sending the first packet and receiving a response, and that will inform the source about the delay of the packets. This is an example of a trace route between a source node and a destination node. You will notice that the results are showing the router and 3 delays measurements, and these are the 3 packets. This will give information about the clue delay, the transmission delay, the propagation delay about the network, and it can tell, or you can tell, how long it's going to take for these packets to be sent, and you can diagnose the network, for example, and see where the problem is. You will notice that sometimes these delays are different. They're not increasing. Sometimes the second one is less than the previous one. This might be because the traffic at that point in time in the network was, for example, low. There's no much queuing delay. There's no much traffic. So this might affect the delays you get as a result from that program. As we discussed before, every router has a buffer or a queue, and every queue has a size. So if the arrival rate is very high compared to the link bandwidth or transmission rate, then packets will start piling and being added to the queue. If the packet arrival rate or packet being arrived exceed the size of the queue, there's no much space to put these new packets, so the new packets has to be dropped and marked as lost. In that case, these lost packets can be retransmitted by the source or by the previous node, or maybe just for we can forget about it and not transmitting it at all. Based on all this, based on the router techniques we used and how the network is being set up and how important is that packet. Let's move on and look at the throughput. What is meant by the network throughput or a link throughput? A throughput is the rate at which bits transferred between sender and receiver. This is measured as bits per second. We have 2 types of measurements regarding the throughput. We have instantaneous throughput, which is the rate at a given point in time. We have the average rate, which is the rate over a longer period of time. Let's look at this example down here. We have a server and we have client. The path between the server and client have one router. They're not directly connected, so they have to go through a router. Every connection has a link, and every link has a capacity. This capacity is simply how many bits can be transmitted in second on that link. Think of this as you're pumping fluid through pipes. This is how much fluid can go through this pipe, which is by the thickness of the pipe, and the same thing in here. Let's go back and look at this in details. Again, we have the server and we have the client. You can notice that the sizes are different. That means the pipe is thinner or thicker. The thicker the pipe, the more fluid you can send, and the same thing, the higher the throughput, the more bits you can send, because this is, again, how many bits you can send in a second. Now, let's assume we have, this is a 2 megabit per second link, and this is 5 megabit per second. This is very nice, because the server can send maximum of 2 megabit per second, and these 2 megabit per second will get to the queue. And remember, the transmission rate here is 5, which is greater than 2 megabit per second, so all these will be put direct, and this link can handle all this traffic. Now, let's look at this example. Assume this link is 5 megabit per second and this one is 2 megabit per second. Now the server will send the full capacity of 5 megabit per second. When these packets arrive at the router has to go ahead and send those over a 2 megabit per second. This is more than what this link can handle. Therefore, if we send this much traffic, the router has to start piling these because the transmission rate cannot handle this much traffic, and this introduces us to what we refer to as the bottleneck link, which is the link on end-to-end path that constrains end-to-end throughput. Therefore, according to our example here, this link is our bottleneck link because this prevents us to send the packets in the full capacity of that link. And this is very important when you design your network. You have to make sure that you're not wasting your transmission, because if you keep pumping water or fluid in a pipe and the container cannot handle that much fluid, it will start spilling the fluid, and the same thing in here. If you're sending too many packets but the router cannot handle those many packets or cannot release those packets on the next link, so that it will start dropping, so that will waste your time because you have to retransmit the packet again. Let's look at this example here. We have the network core, which consists of a router and set of links. Let's assume we have 10 servers and 10 clients. All these are connected through the core. Let's assume we have the link from the server to the core. It has a link throughput of our server. We have the network core R, and we have the client server or the client connection bandwidth RC. The end-to-end throughput in here is measured by the minimum throughput among them all. Now if you look at the core here, based on the number of connections, we have to divide, to be fair enough, and divide that rate or transmission rate among all the currently active senders. If we assume that all of these servers are sending at the same time, therefore the link capacity or the link throughput at the core will be equal to R divided by 10, and that is actually the capacity that this core can send to. So every one has to send using that specific capacity. So everyone will use 1/10 of that link throughput. Let's go through a set of examples and see how we can measure these delays and throughputs. Consider a single router transmitting packets. Each packet has a length L over a single link with transmission rate R megabit per second. Let's assume that the length of the packet is 4,000 bits and the link has a capacity or transmission rate of 1 megabit per second. That means we can send 1 megabits in each and every second. So the question is, what is the transmission delay? The time it needs to transmit all of the packet bits onto the link. Remember that the transmission rate is simply move the packets from the queue to the link, not all the way to the destination. To figure this out, the transmission delay is simply equal to L divided by R, which is the number of bits divided by bits per second, and that will give me the transmission in seconds, and we can convert it to milliseconds. So let's look at R. R equal 1 megabit per second, which equals 1000 kilobit per second, which equals bits per second. So to do the math, transmission delay equal to 4000 divided by, which equals to 4 seconds, which equals to milliseconds. So the transmission delay equals 0.4 milliseconds. Now the second question is, what is the maximum number of packets per second that can be transmitted by the link? Again, we have a link of 1 megabit per second, which is equal this, and each packet is 4000 bits. So to get this value, simply we will go ahead and divide the rate, number of packets, equal rate divided by L, and that will give you and that will give you 250 packets can be transmitted using that rate per second. Let's look at another example. Consider this network in the figure where we have a client and a server. These are connected through two routers, and as you know, between every node and another we have a link. Each link has a rate and it has a length. We'll be using these to measure a set of delays. We need to find the end-to-end delay, including the transmission delay and the propagation delay on each of the three links. But for now, we're going to be ignoring the queuing delays and any processing delay. The propagation delay is 3 multiplied by 10 to the power of 8 meter per second, and the packet length is 4000 bits, and we need now to figure out the transmission and the propagation delay on each link to be able to measure out the end-to-end delay. Let's look at the first link here, which is this one. The link has a rate of 100 megabit per second, so the transmission delay equal, remember, L divided by R, which equal 4000 divided by 4000 bits, which is the L from the previous lecture, divided by 100 megabits kilo, and this is number of bits, and that will give you a value of 0.04 millisecond. The propagation delay of that link is propagation equal to the distance divided by the speed, which equals 3 divided by the speed, 3 multiplied by 10 to the power of 8. Remember, this is meter per second, so we need to convert this 3 kilometer to meters, multiplied by 1000. So that will give you 3000 divided by 3 to the power of 8, and that will equal to 0.0001 seconds, which equal to milliseconds. So that's for the second one. Continue our calculations. Let's look at the second link. The second link is the same. We're going to talk about transmission delay and propagation delay. So transmission delay equal to L divided by R, and here L is the same, which is 4000 bits, divided by the rate is 1000, and that equals to 4 milliseconds. The propagation delay equal to 500 kilometers convert to meter divided by 3 to the power multiplied by 10 to the power of 8, and that will give you a value of 1.67 milliseconds, and that's the propagation delay of the second link. Finally, the transmission delay and the propagation delay for the third link can be calculated as, so this is 2, this is 1, 1. Let's say delay transmission equal of the third link, which is the same. We have L divided by R, which is equal 4000 divided by and that will give you a value of the same as this one, 0.004 millisecond, and propagation delay equal to distance divided by S, and that equals to distance is 2 kilometers, which is 2000 meters divided by 3 multiplied by 10 to the power of 8, and that equals to 0.00067. And now after we got all this, now we can do the total or the end-to-end delay equals all these delays. That's the delay plus the propagation delay of the first link plus the delay of the second link, or the transition delay, plus the propagation delay of the second link, plus the transition delay of the third link, plus the propagation delay of the third link, and that will equal to 1.73 milliseconds. So based on this, we can say that the end-to-end delay of this network should be 1.73 milliseconds. Our third example is about end-to-end throughput. Let's consider 4 different servers that are connected to 4 different clients over 4 3-hops paths. So we have the core here, and we have these servers, and here are the clients. The 4 pairs share a middle hop with a transmission capacity of 100 megabit per second. The 4 links from servers share the capacity of 80 megabit per second each. So each of these links has a link bandwidth of 80 megabit per second. All the links on the other side, from the router to the client, have 60 megabit per second as a link transmission or the rate transmission capacity. Now the question is, what is the maximum achievable end-to-end throughput in megabit per second for each of 4 client to server pairs, assuming that the middle link is fair shared. Fair shared means that since we have 4 transmission, concurrent transmission, so we have to go ahead and divide that between 4. That means shared R divided by 4 equal 100 divided by 4, and that give us 25 megabit per second each. So each of these links will go through at 25 megabit per second each. So the maximum achievable end-to-end throughput. Remember, the achievable throughput is simply you need to send the packets without losing traffic. Look at this here. This one will send 80, but the problem is not here. The problem is here. This link cannot take more than 25 megabit per second. So if you send using the 80, you're going to lose packets right here because you're overflowing the network. You're pumping too much fluid. Again, consider the pipes. You're pumping too much fluid that this link cannot handle. Therefore, let me go back and say 25 megabits is the problem. Look back down here, we have 60. 60 is still greater than that, but the problem here, if we push 25 megabits from here and push 25 from here, the only thing that comes out is 25. Even if you push 80, this is 25, so this cannot take more than 25 because this is limited to 25, that link. Therefore, I can say that the maximum achievable throughput is 25 megabit per second, which is simply the bottleneck link for these sessions. So that's going to be 25 megabit per second, which is the core. This should conclude this lecture. We covered the delays, different types of delays. We covered the throughput, and we go through simple example to see how we can calculate these types of delays. With that, I conclude this lecture, and I will see you next time.